Hey guys, so in this video we're going to put a lot of what we've been doing with parametric equations together and apply it to a real world situation. So a lot of the mechanics that we've been developing in the last two videos are going to kind of come together in this video to answer a small scale real world problem. So one avenue that we often use parametric equations in is in projectile motion. So I'm going to show you a couple of relationships that are always true. In fact, you'll develop them when you take a elementary physics course and also when you take calculus. So I'm going to hand wave over a couple of things, but I'll try to explain a little bit of where these equations come from so that you understand what they mean and how we're going to apply them here. So when we're talking about projectile motion, parametric equations often crop up and are defined in terms based off of some parameters that we're going to plug in. One of which being an angle, theta, is the angle of elevation that a projectile is fired from into the air. And then we're going to define the horizontal distance and the vertical distance in terms of the parameter time. So I'm going to just draw a little diagram so you get a sense of kind of what we're talking about here. So I'm going to draw a little cannon. Okay. And in my little cannon, we're going to fire a projectile out. So little cannonball gets fired out the end. So a couple of the things, the initial speed that the cannonball leaves the muzzle of the cannon, that's what we call V0, or the initial velocity. We're going to define the angle that it's fired at to be theta. That angle is measured with the horizon. So it's an angle of elevation. And then we are also going to define an initial height. So say, I don't fire it from ground level. So say my cannon is about a foot high. So I would say that its initial height would be 1. So I'm going to call that h with the little subscript 0 for initial height. And there's one other parameter that we're going to need. And it's actually the gravitational constant on Earth. So the gravitational constant on Earth is about 9.81 meters per second squared. It's an acceleration due to gravity. Or if we're talking about feet, it'd be 32 feet per second. So it depends on what unit of measure you use, but that is a constant that's always true. So those are the elements that we're actually going to need. And that's all the stuff we'll really need to get these equations going. So x is going to be the horizontal distance that this cannonball travels t seconds after it leaves the cannon. So on my graph, that x is representing essentially just so that the path of this object is going to follow a parabolic curve, and then it's going to come crashing back to Earth. So at any point along its path, that's what I'm representing by x. It's the distance from its initial starting point to where it currently is, t seconds after it's left. That's x. And the whole reason for this V0 cosine theta is that initial velocity times cosine theta is the proportion of this angular speed that moves in the horizontal direction. So that's the V0 cosine theta part. That's how much of this velocity is being moved horizontally. Some of that velocity is also being moved vertically. And because distance is equal to rate times time, if this is the horizontal rate and I multiply it by time, that's going to give me horizontal distance. Okay. Now, y is going to be the vertical height at this position, wherever it is, t seconds after it leaves. So you might expect that I'm going to get t times the vertical velocity, so t times v0 sine theta, and you'd be right, but there's an added wrinkle in there. So yeah, we have that component that I would have expected, t v0 sine theta, so that's the vertical component of that initial velocity. But I have this second term, this 1/2 negative 1/2 g times t squared, and then I have a third term h0. So the h0 is the initial height, so it makes sense that I'd add that initial height on because that's just going to shift me up. But what about this middle term? Well, that's the gravitational pull of the Earth. Now, since I have an initial vertical component of velocity directing me upwards, the gravitational pull is pulling me downwards. That's why this component is negative, because it's pulling me in the opposite direction from what I was initially fired. As to the why is it 1/2 times this gravitational constant and then times t squared. That's the part where I'm going to do some hand waving, because you have to understand some physics or calculus in order to make that explanation meaningful. So I'm going to hand wave past that, and we're just going to use this relationship. We're going to take it as assumed to be true. And the problem that I want to look at or apply this concept to is, say I have a projectile fired from the ground at an angle of elevation of 21 degrees with an initial speed of 62 meters per second. I want to see how far will this projectile move overall. So this is why I need some understanding of parametric equations. I want to know how far it's going to go horizontally. So let's understand first what it's saying. So I'm going to let this line be the ground. Okay, and this projectile is being fired from this point over here, and it's being fired with a initial velocity of 62 meters per second at an angle of 21 degrees. And my angle is a little big, but it's okay. It's just a diagram, 21 degrees. And what I'm going to expect is that this projectile is going to fly through the air and then eventually come back to Earth and land. And my question is, how far is it going to make it? So what is this distance? Okay, so I'm going to let, we'll call that D for total distance. Okie dokie. Okay, so we can fill in a couple of things. We know that based off these equations, this projectile's path is going to be defined by T times 62 cosine of 21 degrees, and Y is going to be T times 62 cosine of 21 degrees, sine of 21 degrees, because it's vertical, minus 1/2 times the gravitational constant, 9.8. Now I know to use 9.8 and not 32 because my initial velocity was in meters per second. So I'm going to use the meters defined version of gravitational constant, which is 9.8, not the feet one. So that's 9.8 times t squared plus h0. Now it does say that I was fired from the ground. So if I'm leaving the ground, the height of the ground initially would be 0. So my initial height is 0, so I don't have to add anything in there. So I know that this is the path of the object. Now my question is about horizontal distance. So I think to use this relationship, but I don't know the t, and that's where the second parametrically defined equation comes in. Because if I want to know the total distance that I traveled horizontally, I need to know when this projectile hits the ground again. So I need to know when is its height, or when is its y value 0. If I'm able to find the time that it takes it to fly through the air and then re-hit the ground, I'll know t. I could then take that t, plug it back in for x, and I'll know the total distance traveled. So I'm using that parametrically defined relationship to do that. So that's what we're going to do. We're going to plug 0 in for y, get t times 62 sine 21 degrees minus, so this is going to be 4.9 t squared, which is half of 9.8. And I need to solve this for t. So if I factor this, I get, as a common factor, t, 62 sine of 21 degrees minus 4.9 t. So either t equals 0, which is, we can recognize based off of my little diagram here that that's actually the start of the problem. So I'm going to ignore that solution. T equals 0, I'd reject as the one I want. It is a solution, but it's not the one I'm looking for. I'm looking for this other one, which would happen when t is equal to 62 sine of 21 degrees divided by 4.9. Okay, and then I could go to a calculator to calculate that value. I'm going to make sure, as my calculator is loading, if you're checking this in a calculator yourself, you want to make sure that you are in degree mode. So I am in degree mode right now, so that's convenient. And I'm going to type 62 sine of 21 degrees divided by 4.9. So it gives me 4.53. Okay, 4.53. That is 4.53 seconds. That is the time that this projectile will stay airborne before it crashes back to Earth. So now that I know the time, I can answer my question for the total distance. Distance is the x measure here would be 4.53, because that's the time it takes to end this trip, times 62 cosine of 21 degrees. So I'm going to go back to my calculator. Slide it over so I can see my values. So it's this number times 62 times cosine of 21 degrees. So it should travel 262.46 meters. So 262, I'll say 262.5. So the answer to my question is 262.5 meters. So this problem is an example of how parametrically defined equations can crop up in real-world problems, and how we can utilize different components of these parametric defined equation parameters to get answers to questions. So like say you were designing a cannon to fight someone who's in a fortified position and you needed to get in there. You could use this kind of mathematics to determine precisely what angle you need to fire your cannon at to get to a certain distance in the battlefield. You could use this in terms of mechanics if you're playing football or basketball, what angle you should be shooting a basketball to make it into the hoop. And we have an intuitive nature of this, but this ascribes some formal mathematics to help us describe this problem and calculate the exact values overall. Okay, so that's one application of parametric equations. There are others. Another application we'll look at is what happens if we have a parametrically defined solution to a linear system.